Hey everybody, Trey here, and welcome to my 2024 tornado season forecast. It's the end of February and meteorological spring is just a few days away, so it's time to answer that burning question that every storm chaser and meteorologist has of what tornado season might look like this year in the US. We did our inaugural tornado season forecast last year, and I was fairly pleased with the feedback and results, so let's do the same thing this year. We're going to make a forecast for tornado frequency and distribution in the U.S. for the March through June timeframe, basically the climatologically favored period for enhanced tornado activity in the U.S. We're not looking at hail or damaging wind, just tornadoes, and more specifically, how many and where those tornadoes will occur. We're also going to be looking only at the typical areas that see tornado activity each year: the entire Great Plains, the Midwest, the Mid-South, the Southeast. We're not going to be looking at places like the West Coast or the Northeast where you might get a couple oddball tornado events each year, but where normally you won't see much, if any, tornado activity during the spring. So we're going to talk about a few different factors that modulate tornado frequency and distribution in the U.S. each spring, how those variables are looking right now, and how they're expected to change over the next few months. And then we'll take a look at some analogs, years with similar background conditions, to see some possible outcomes of what might happen this spring in the tornado department before making our final forecast. Just a couple notes before we dive in. I'm going to put a link to last year's tornado forecast video in the description box below. I plan on reviewing all the concepts we talked about in last year's video in this video, but if you have additional questions or want some clarification, head on over to that video for more. And as always, I'll put a link to any journal articles or important websites I use in this video in the description box below, so you can do some research on your own. Also, keep in mind that this is not an exact science. Tornadoes are hard to predict just a few hours ahead of time, let alone months in advance like we're doing here. And as we've discussed on the channel ad nauseum, tornadoes are often influenced by features that occur on a much smaller scale than the modulating factors we'll be discussing in this video. But we can at least make a highly educated guess regarding what might happen this season based on the factors we'll discuss, which have been shown in peer-reviewed research to impact tornado frequency and distribution in the US on some level. So without further ado, let's go ahead and get started. Just for some context, here is where our tornado report count stands so far in 2024. We're sitting just below average for the year up to this point, as shown by the red line. The black line is our yearly average. That's a pretty stark contrast to last year, in which we saw the most active January through March period on record. This year, most of our tornado reports have been confined to the southeast. We've had a few events elsewhere, such as the historic Wisconsin tornado event back on February 8th, but most of the action has been down on the Gulf Coast and eastern seaboard. This, plus our slightly below average start, is not all that surprising given the background conditions that have been in place. We'll expand on this in just a second. So if you recall from last year's video, we talked about three main factors that tend to modulate tornado frequency and distribution in the US: global climate teleconnections, sea surface temperature anomalies in the Gulf of Mexico, and drought in the elevated mixed layer source region. Let's start off with global climate teleconnections, and we're going to use one in particular called the El Niño Southern Oscillation, or ENSO. ENSO involves sea surface temperature anomalies in the equatorial Pacific, basically the departure from average of the sea surface temperatures in the portion of the Pacific Ocean that lies along the equator. As you may know, ENSO has different phases. In basic terms, if the sea surface temperatures in the equatorial Pacific are warmer than normal, as in the top panel, we are in an El Niño phase, whereas if the sea surface temperatures in the equatorial Pacific are cooler than normal, as you see on the bottom, we are in a La Niña phase. And if the sea surface temperatures in the equatorial Pacific are about average, we are in a neutral phase. Now, there are several indices one can use to quantify ENSO phase, and perhaps the most common is the Oceanic Niño Index, or ONI. The ONI is a 3-month running average of sea surface temperature anomalies in the Niño 3.4 region, which is the portion of the equatorial Pacific between 5 degrees north and south latitude and 120 and 170 degrees west longitude. Again, the ONI uses a 3-month running average, which means that instead of measuring the sea surface temperature anomaly in each individual month, the ONI averages the sea surface temperature anomaly over each consecutive 3-month period. For example, January, February, March, then February, March, April, then March, April, May, and so on. This helps smooth out random fluctuations that might occur in the data. If the ONI is greater than positive 0.5 degrees Celsius for a single 3-month period, we would be in a warm phase, and if the ONI is less than or more negative than negative 0.5 degrees Celsius for a single 3-month period, we would be in a cool phase. And if the ONI is between negative 0.5 and positive 0.5 degrees Celsius, we would be in a neutral phase. If we're in a warm phase for more than 5 consecutive 3-month periods, we'd be in an El Niño. If we're in a cool phase for more than 5 consecutive 3-month periods, we'd be in a La Niña, and the same thing applies for the neutral phase. Of course, ENSO is a cyclic phenomenon, hence the name El Niño Southern Oscillation. We oscillate back and forth between El Niño, neutral, and La Niña phases, as you can see on this graph of ONI dating back to 1950. So where do we stand with ENSO right now? Here's a map of our current sea surface temperature anomalies across the globe. The yellows and oranges indicate warmer than normal waters, and the blues indicate cooler than normal waters. And you can see in our Niño 3.4 region, we have widespread above average sea surface temperatures, with even some pockets of 2+ degrees Celsius above average water. This has been festering for quite some time now. After a multi-year period of La Niña conditions, we flipped into an El Niño state around the middle of last year, and that's where we find ourselves right now. In fact, we are in a strong El Niño, which is when that ONI value exceeds positive 1.5 degrees Celsius. That's been the case for the last few 3-month periods, with the November, December, January ONI coming in right at positive 2 degrees Celsius. But that is expected to change as we head into spring 2024. Here's a graph that shows a bunch of climate model forecasts of ENSO in 2024, with each successive 3-month period on the horizontal axis and ONI on the vertical axis. Here's the latest ONI observation for November, December, January, registering at almost positive 2 degrees Celsius, and here's the observed value for January only, coming in at positive 1.78 degrees Celsius. So it does appear that those warm anomalies are starting to decline, and all models are forecasting a continued decline through the spring. It looks like we'll still be in the El Niño phase during March and April, but it will be rapidly weakening, and by May and June we should be back within a neutral phase before emerging into a weak La Niña by midsummer. This is also reflected in the Climate Prediction Center's latest bar graph of ENSO probabilities for the year. Once again, time is on the horizontal axis in the form of our 3-month periods, and the percent chance of occurrence of each ENSO phase is on the vertical axis. The orange bars represent El Niño, the blue bars represent La Niña, and the gray bars represent the neutral phase. We start off with very high probabilities of El Niño continuing through at least the time period centered on April, and then we see those probabilities for neutral ENSO shoot up to about 80% by the April, May, June period, and that should last through the remainder of the spring season before La Niña takes over in the summer. Now these are just probabilities, so the onset of neutral conditions may occur a bit earlier or later than expected, but for now it looks like that transition to neutral should occur around May. So how does all this impact the atmosphere? Well, ENSO tends to modulate the position and amplitude of the jet stream, especially over North America, as you can see on these conceptual models of the atmospheric impacts of El Niño on the top and La Niña on the bottom. Now these graphics show the impacts during the winter, but the same patterns generally hold for spring. In an El Niño phase, the jet stream tends to be a bit more muted and shifted farther south. That's why this winter we've seen the majority of our severe weather events confined to the Gulf Coast region. You can imagine what impact this might have on springtime severe weather as well. A more muted, less intense jet stream during El Niño means a less intense low-level response, and therefore a slightly less favorable situation for widespread severe weather, including tornadoes. On the other hand, during La Niña, the jet stream is far more amplified with a lot more troughs impacting the U.S., which means severe weather, including tornadoes, tends to be more frequent and widespread, even though in the winter those troughs can get shunted off to the east, drying out the southern U.S. And the neutral phase is somewhere in the middle. These ideas have been supported by ample peer-reviewed research, including this paper by Cook et al. 2017, who tried to find a linkage between ENSO phase and U.S. tornado outbreaks in the winter and early spring, basically January through April. Let's take a look at their figure 3C and D, which show normalized tornado counts for both March and April in the U.S. Basically, they split up the area east of the Rockies into a grid, tallied up all the tornadoes in each grid box during each month for each ENSO phase, then divided those counts by the number of months that each ENSO phase occurred during the study period, which was 1950 to 2010. For example, let's say a certain grid box had 10 total tornadoes during all El Niño marches in the study, and that there were 20 marches where El Niño was present during the study period. You divide 10 by 20 to get a normalized tornado count of 0.5 for that grid box for El Niño marches. For each of these figures, El Niño is on the top left, La Niña is on the top right, and neutral is on the bottom left, and the warmer the color of the contour, the higher the normalized tornado frequency within that contour. For March, we can see that during El Niño, normalized tornado counts are typically lower than for both La Niña and neutral marches, with no real apparent hotspot, except maybe down along the Gulf Coast in the Louisiana-Mississippi area. In El Niño Aprils, we see a similar decreased tornado frequency versus La Niña and neutral Aprils, with the most favored areas occurring in the southern plains and southeast. However, as mentioned earlier, the farther we go into the season, the closer we're going to get to neutral conditions, and that changeover to neutral may very well occur during the back half of April, So if that does happen, we could transition into a slightly more favorable pattern for tornadoes with a major focus on the southern plains and perhaps the Midwest. In fact, the highest normalized tornado frequencies occur in the southern plains during neutral Aprils. Now, as we know, ENSO is not a static phenomenon, which can be a drawback to using the individual ENSO phase during each month to predict tornado activity in the US. Instead, research by Lee et al. 2016 showed that looking at how ENSO phase evolves throughout the spring may do a better job at helping us predict tornado frequency and distribution in the US. They looked at several different ENSO progressions and how tornado outbreak frequency and distribution changed among them. This spring's expected ENSO progression most closely follows what Lee et al. Dubbed the early terminating El Niño, in which a weak El Niño remains through peak season, but quickly transitions into a neutral and eventually La Niña state after peak season. Here are their findings taken from the supplementary data accompanying their 2016 paper. Conceptual month-by-month sea surface temperature anomalies for an early terminating El Niño are on the left. It's not a perfect match. In their model, cold anomalies fully take over by May in the equatorial Pacific, which is a bit premature for what's forecast this year, but it's a decent match nonetheless. On the right are gridded probabilities of tornado outbreaks for each month, February through May, in an early terminating El Niño period. The shaded regions represent areas with an elevated probability of seeing a tornado outbreak, with darker colors representing higher probabilities. Grid boxes with black dots indicate that those probabilities are statistically significant. In March, not much of note, maybe a slightly enhanced probability of tornado outbreaks from the eastern plains into the Ohio River Valley, but nothing statistically significant. April is where we start to see some notable trends. You'll notice a couple probability maxima, one centered on southern Oklahoma into North Texas, and one up in the Kansas, Nebraska, Missouri, Iowa confluence area. The early terminating El Niño tends to be its most influential in May, with a large area of heightened tornado outbreak potential from the central plains into the upper Midwest, and another area from southern Kansas into Oklahoma. Now, June is a bit more up in the air as the correlation between ENSO and tornado activity in the U.S. weakens the farther you go into the season. In other words, ENSO seems to influence the weather patterns over North America most in winter and early spring, March and April, but that influence weakens a bit in May and especially into June, making it difficult to use ENSO as a predictor for June tornado activity in particular. We'll have to rely a lot on our analogs to give us an idea of what June might look like, but overall we see some promising trends for this spring, at least from a storm chasing perspective based on these studies. It looks like we might start off a bit on the slow side in March, with one caveat in the short term which we'll discuss in a bit, before picking it up quite a bit in April and May with potential hotspots in the southern plains and Midwest. As you may know, there are a bunch of other teleconnections that impact weather across the globe, the MJO, the NAO, the AO, etc. The problem with many of these other teleconnections is that they fluctuate on smaller timescales than ENSO, which makes using them as a variable to forecast tornado frequency and distribution months ahead of time, like we're doing in this video, almost impossible. ENSO changes quite predictably, allowing us to get a good picture of how it will evolve many months into the future, making it quite useful for long-term tornado forecasts. Also, based on research, ENSO appears to have some of the strongest influence on U.S. tornado activity of any of the climate teleconnections. Alright, let's move on to Gulf of Mexico sea surface temperature anomalies. As you know, the Gulf of Mexico is the source of our moisture for severe weather events in the U.S. As low-level flow turns out of the south ahead of developing surface lows, that warm, moist, unstable air mass over the Gulf gets transported northward into the U.S. to set the stage for severe weather. We also know that warmer air holds more moisture. Intuitively, if the sea surface temperatures in the Gulf of Mexico are warmer than normal, the air mass atop the Gulf that gets advected into the U.S. is warmer and can hold more moisture and thus is more unstable, and the potential for severe weather, including tornadoes, increases. On the other hand, if the sea surface temperatures in the Gulf are cooler than normal, the air mass that gets advected northward is less unstable, and therefore the potential for severe weather, including tornadoes, decreases. This is supported by Molina et al. 2016. In their Figure 3, they illustrate the difference in instability anomalies between cooler than normal Gulf waters on the left and warmer than normal Gulf waters on the right. Mixed layer CAPE, which is our main measure of instability, tends to be near or below normal when Gulf of Mexico waters are relatively cool, as shown by the blue colors, and above average mixed layer CAPE is much more widespread when Gulf of Mexico waters are relatively warm, as shown in red. Here's where we stand now. Kind of a mix of anomalies with colder than normal waters across the far northern and eastern Gulf and warmer than normal waters across the western and central Gulf. Quite a warm pocket there off the southeast Louisiana coast. Overall, I'd say we're about average to slightly above average across the entirety of the Gulf, and with El Niño easing its grip over the next couple of months, that jet stream will start to shift north a bit, allowing for less cold frontal intrusions and convective complexes over the Gulf, which have been probable culprits for the cooler than normal areas, especially those off the Florida coast. As a result, I'd expect some warming of the Gulf waters over the next few months, as we've seen the last several years, but this is still up in the air, and for now, we'll go with average to slightly above average sea surface temperatures across the Gulf for our forecast, meaning typical to slightly more robust instability than normal seeping inland this spring. Finally, let's take a look at drought in the elevated mixed layer source region. If you followed the channel for any length of time, you probably know what the elevated mixed layer, or EML, is. The EML is that layer of warm, dry, well-mixed air that emanates from the higher terrain out west, western Mexico, West Texas, New Mexico, and areas northward, and gets transported atop the low-level moist layer out east amid westerly or southwesterly mid-level flow. This helps thwart thunderstorm development for much of the day until the cap erodes, and it allows instability to build effectively. However, if the EML is too strong, in other words, if that warm layer is a bit too warm, that can make full cap erosion difficult and can thwart thunderstorm development altogether in a given setup. Persistent, intense drought in the EML source region means hot and dry conditions in that higher terrain out west, which can get transported out east and cause chronic capping issues for severe weather events in the plains and Midwest, limiting overall tornado potential. Therefore, we want to see generally limited drought across the EML source region, as that will keep the EML in check, if you will. Here's our current map of drought across the U.S. from the University of Nebraska's Drought Monitor. The darker the shade of red, the more extreme the drought is, and we're not doing too bad. We've seen quite a bit of drought eradication across much of the actual plains over the last several months thanks to a wet winter. Out west in the EML source region, we are dealing with some more severe drought, especially across southern portions from New Mexico into West Texas, but overall this isn't of massive concern. Let's put it this way, we've seen a lot worse in recent years. For example, here's the same map from March 2nd, 2021, and if it looked like this right now, I'd be very concerned. You can see much more widespread severe drought across the higher terrain out west, and this was a year that saw a fairly quiet spring season. So from a tornado perspective, this year's drought situation going into the season looks pretty good. Now let's look farther out into the season. This is the Climate Prediction Center's seasonal drought outlook valid from now through the end of May. Areas in brown are where drought is expected to persist, and areas in yellow are where drought is expected to develop. We do see some continuation and perhaps worsening of the drought across southern portions of the EML source region, so we'll have to monitor that as we go into the season. But right now it seems to me that the overall drought situation does not look like it will significantly impact EML strength. Plus, as we start to get higher amplitude troughs moving into the U.S. as El Niño weakens, the forcing associated with those troughs might be stronger, and stronger forcing can more efficiently erode any capping associated with the EML. Alright, now for the fun part. Let's dive into some analog years. That way we can see what happened tornado-wise in years that had similar background conditions. So I went through the database going back to 1950 with a goal of selecting years that had similar ENSO progressions, Gulf of Mexico sea surface temperature anomalies, and drought out west. That means years that started off in a moderate to strong El Niño and transitioned to neutral during the season, average to slightly above average Gulf of Mexico sea surface temperatures, and what I called low to moderate drought in the EML source region. Gulf of Mexico sea surface temperatures were given the least weight in my analysis, as they have the weakest correlation to U.S. tornado activity of the three variables we studied. So if a potential analog year was a good match for ENSO progression and drought, but not Gulf of Mexico sea surface temperatures, I still considered it a good analog, although years that showed good similarities to all three variables were considered the best. Now remember, this is a subjective exercise. I didn't use some algorithm to pick out these analogs, so there may be some years that I threw out that you might put into your analysis or vice versa. Just a couple caveats. First, the database of sea surface temperature anomalies only goes back to 1982, so we'll have to disregard Gulf of Mexico sea surface temperature anomalies for any years prior. Also, the archive of drought monitor maps only goes back to 2000, so to analyze drought for analog years, we're going to use something called the Palmer Drought Severity Index, which is a measure of how prolonged dryness or wetness is in a region, rather than a more short-term look at drought as exhibited in the drought monitor maps. The archive of Palmer Drought Severity Index maps goes back to 1950, which is useful for our purposes. For years after 2000, I'll also show the drought monitor map heading into the season. This is our current Palmer Drought Severity Index map, and you'll notice it looks a bit different than our current drought monitor map. Yellows and oranges represent long-term dryness and, in turn, drought, while greens represent abnormal long-term wetness. Areas shaded in black have missing or incomplete data. Whereas we saw areas of more intense short-term drought across the desert southwest into West Texas, we see that, over the long term, these areas have been near normal, with some smaller regions even experiencing abnormal wetness. So in comparing this year's drought to that of analog years, I looked for years that had similar, generally neutral drought conditions across the EML source region. I did also include years that had more widespread abnormal wetness as good analogs in the drought department, because the linkage between widespread extreme drought and a stronger EML is much stronger than the linkage between widespread abnormal wetness and a weaker EML. In other words, just because the EML source region might experience prolonged abnormal wetness does not mean there is going to be a limited or non-existent EML. So in my research, I identified 8 different analog years that had similar background conditions to this year. We're going to discuss 6 of them here. 2 of them were only loose matches, so I decided to omit them from this video. Some analogs were better than others. We'll go over the best ones first, and then some of the good but not quite as good ones afterward. The closest analog I could find in the database was 2016. We began in a very strong El Niño, even stronger than what we're seeing this year, but quickly transitioned into neutral conditions around May before dipping into La Niña by midsummer. Sea surface temperatures in the Gulf of Mexico started the season around average to slightly above average in spots, and while the plains themselves may have been experiencing a prolonged moist period, most of the EML source region was experiencing fairly neutral drought conditions going into March, with little to no short-term drought to speak of. 2016 was a bit of a below-average season tornado-wise. March was fairly active, with a lot of activity concentrated from the Mid-South into the Gulf Coast states, and a bit of early-season activity in the Midwest. We then went into a well below average April with a good chunk of the activity centered around Oklahoma and Texas. May was slightly below average as well, although May 2016 is considered by storm chasers to be one of the best stretches for tornadic activity and overall storm chasing in recent memory. Basically, from May 7th through about May 26th, you had event after event produce some incredible tornadoes in the central and southern plains, including the Southern Oklahoma outbreak on May 9th, the Dodge City, Kansas Tornado Fest on May 24th, and the Chapman, Kansas EF4 on May 25th. The season was capped off by a very slow June with only scattered activity in the high plains and Midwest. Another really good analog for this year is 1998, in which we again underwent that classic early terminating El Niño pattern, starting off with a strong El Niño before transitioning into neutral by mid-spring. The EML source region and the plains themselves had seen quite a bit of prolonged wetness leading up to the season, so we can check the box for a favorable level of drought for spring 1998. But unlike 2016, Gulf of Mexico sea surface temperatures started out a bit cooler than normal. Overall, March through June 1998 was quite a bit above average in the tornado department. Tornado activity in March was confined mostly from the Carolinas into Florida, except for a rare early-season significant tornado event in southern Minnesota, in which a single supercell produced 14 tornadoes, including an F4 that hit the town of Comfrey on March 29th. April was about average, with most of the activity occurring from the Midwest into the Southeast, including a couple of F5s in Tennessee and Alabama. That preceded an above-average May. Now, the numbers are skewed a bit by a lot of activity in the eastern seaboard states, but a clear corridor of enhanced tornado activity in our more typical areas occurred in the Midwest. Interestingly, not a ton of activity across the central and southern plains, not really any hotspots to speak of in that region. This active May rolled into a hyperactive June, which saw nearly double the climatological monthly average. Lots of late-season tornadoes in Kansas and Oklahoma, and a bunch of activity across the Midwest once again. 1966 also turned out to be a very good analog. We didn't start the year with quite as strong of an El Niño as we have now, and we never actually transitioned into a La Niña by summer, but it still followed Lee et al.'s early terminating El Niño fairly closely. 1966 also had one of the better matches to our current drought, with widespread neutral drought conditions across the entirety of the EML source region. Now remember, back in 1966, tornado reporting and surveying practices were much more rudimentary than they are now, so don't pay as much attention to the tornado counts for 1966, but rather focus on the areas where tornado activity seemed to be enhanced. March 1966 featured some typical southeast activity, as well as some early season activity in the Midwest. That seems to be a bit of a trend with these analogs so far. April saw quite a concentration of activity across Oklahoma and Texas, with some across the Midwest, and May had a pretty typical distribution of tornadoes across the plains with no real notable hotspots. Same thing with June, although we do once again see a good degree of late-season activity from Texas into Oklahoma and Kansas. This may also be a trend that's beginning to emerge in these analog years. Also, notice how we have yet another notable Minnesota event, as we saw in 1998. 1998's was in March, this one is in June, but it is interesting to note that we've seen multiple significant Minnesota tornado events in these analog years so far. These next few analogs were not quite as good as those first three we just mentioned, but were still pretty good matches and worthy of inclusion. The first one of these is 2010, which had the hallmarks of an early terminating El Niño, but we transitioned into La Niña a bit more rapidly than what's expected this year. We did have limited drought in the EML source region and across the entirety of the plains, but sea surface temperatures started off well below average across the entire Gulf of Mexico. If you're a storm chaser, the mention of 2010 should pique your interest big time. 2010 was another above-average season and had a lot of impressive events, including the Yazoo City, Mississippi EF4 on April 24th, and back-to-back high-risk tornado outbreaks in Oklahoma on May 10th and May 19th. Right away, you can see where some of the hotspots were that spring. 2010 began with a very quiet March, just a smattering of activity across the southern states, and April was a bit below average as well, although we had quite a bit of activity centered on the Mid-South and Southeast. Some early season events across the Central High Plains as well. Then the switch flipped in May with a ton of activity in Kansas and Oklahoma, as well as some across the Northern Plains and Mid-South. Interestingly, the Midwest remained very quiet until June, which was another well above average month thanks to widespread tornado activity, including several significant tornadoes from the Northern Plains, including Minnesota again, all the way down into the Midwest. By now we're seeing some pretty good trends emerge, especially focused on the Midwest and Central to Southern Plains. 1973 was similar to 2010 with a little bit too rapid of a transition to La Niña. However, it saw limited drought and even prolonged wetness across a vast chunk of the U.S., including the EML source region. Now, just like 1966, we won't pay too much attention to the overall numbers, but with tornado reporting practices still archaic at this time, the fact that we have over 700 recorded tornadoes in the database, which is almost average, suggests that this was a hyperactive season with likely a lot more tornadoes than what are logged here. March was right around average with quite a bit of activity across the southern states, especially Texas. Things picked up in April with a good mix of activity from the Gulf Coast into the Midwest before an active May, an unusual amount of activity across the southeast this late into the season. It seems as if tornado activity in May was displaced a bit farther east than usual as a whole. We closed out the season in June with a lot of activity in the Midwest and once again quite a bit of late season activity from Oklahoma southward. Our final good analog is 1995. This year did feature an early terminating El Niño, but we started off with a much less intense El Niño than in 2024 and in the other analogs. However, Gulf of Mexico sea surface temperatures were right about average, and neutral drought conditions were in place across much of the EML source region, making 1995 a pretty good match. Spring 1995 was an average to slightly above average tornado season, with another example of abundant activity in the southern plains and in the Midwest. March was fairly quiet except along the Gulf Coast, as was April, with most of the activity confined to the southern states. Quite a bit of activity across Oklahoma and Texas, as well as Louisiana and Mississippi. May was the complete opposite, well above average with ample activity from Kansas into Texas and a major hotspot including a lot of significant tornadoes from the Midwest into the Ohio River area. June remained active in the southern plains, especially across the western half of Texas into Oklahoma. A well-documented outbreak occurred on June 8th in the Texas Panhandle that included the infamous Pampa F4. I also found two other analogs, 2003 and 1988, but they were much looser matches than the other analog years, and therefore I decided to exclude them from this study. Alright, now that we've selected our analogs, let's take a look at the composite upper air pattern in these years. Using the NCEP NCAR reanalysis datasets, I've plotted the composite 500 millibar geopotential height anomalies for all of our best 6 analog years that we just discussed. I gave a little bit of extra weight to our top 3 analogs, 2016, 1998, and 1966, as those were the best matches to especially our expected ENSO evolution for this year, so that's why you see those years listed twice on the bottom. Blues and purples indicate lower than normal heights and, in essence, troughing, while greens, yellows, and oranges indicate higher than normal heights and, in essence, ridging. We'll start off with our entire March through June period, and if you're a storm chaser, this is the kind of look you want to see. We have a large area of below average heights across the southwestern portion of the US, meaning that there's a tendency in these analog years for perhaps stronger troughing across the western US, which, as we know, is favorable for severe weather in areas to the east, such as the central and southern plains. Let's go month by month now. Here's March, and we actually see pretty significant lower than normal heights centered over the southern US, which would mean that most of the severe weather would be confined to the Gulf Coast region, with a lot of colder air seeping down to the north of this apparent troughing. This makes sense, as in a lot of our analogs we saw a fairly quiet March with most of the tornado activity confined to the southeast, save for a few events here and there. Moving on to April, and those lowered heights remain and start to shift back to the west and north a bit, perhaps bringing an uptick in severe weather to places like the Southern Plains, Mid-South, and Midwest by especially the second half of April. May also looks quite interesting as we have a swath of negative height anomalies stretching from the west coast to the northeast, with local maxima off the Southern California coast and over the Great Lakes. This suggests a very active jet stream extending into the southern portion of the country and into the Midwest, possibly hinting at an active to maybe even hyperactive May. The anomalies subside a bit in June, but a plume of lower than normal heights remains across the western half of the country, which could mean a continuation of an active jet stream and therefore active severe weather across the heart of the U.S. So, with all of this being said, what do I think is going to happen this tornado season? I think March will be fairly quiet across most of the U.S. with the exception of the first half of the month. The background pattern is such that we should maintain a fairly active jet stream into the central U.S. for the next couple weeks, which is supported by recent long-range model runs. After this potentially active spurt to start the month in which we could see the tornado count start to increase, I think we'll level off a bit with any tornado activity for the remainder of the month confined to the Gulf Coast. This quiet pattern may seep into April, but I do believe we'll start seeing an uptick in tornado frequency, especially during the back half of April, with a good mix of locations under the gun. This April activity may become focused on the Southern Plains, the Mid-South, and potentially the Midwest. The second half of the season is when I think we'll really flip the switch. I think May is going to be very active with an above average to maybe even well above average number of tornadoes in the U.S. Our analogs and the research we discussed suggest that we may see traditional Tornado Alley light up, especially places like Kansas, Oklahoma, and Texas, and the Midwest may also be a focus for increased tornadic activity, especially in the vicinity of the Iowa, Illinois, Indiana corridor. I also think we'll remain active to very active into June. Again, our ENSO teleconnection is weakest at this point in the season, so we'll have to rely more on our analogs, and many of those analogs show the potential for the Southern Plains to remain unusually active in June. Once again, Kansas, Oklahoma, and Texas may be in for a bit more late-season tornadic activity than normal. Also, a lot of our analogs hone in on the Northern Plains into the Midwest. The Eastern Dakotas and Minnesota into that Iowa, Illinois, Indiana corridor may remain quite active tornado-wise to close out the season. So when you add all that up, a slow-ish start in March and early April before what could be a very active May and June, I think we're in store for an above-average tornado season in the U.S., providing ample opportunities for storm chasers, especially in the back half of the season. And a lot of that activity looks to be focused on the central and southern plains as well as the Midwest. So that's going to do it for this year's tornado forecast. Let me know your thoughts in the comments below. We'll probably revisit this forecast in a video after the season is over to assess how our forecast held up, so stay tuned for that. From a chasing standpoint, I'm very optimistic over what the season may have in store. If we do see an increase in tornadic activity this year, hopefully those tornadoes will stay over open fields to delight us chasers and keep everybody else safe and sound. So with that, thanks for watching, and we'll see you in the next video.